So the first talk is Piyush Kumar, who's going to talk about mixed Wino-Axion dark matter.
So thanks, Bobby. I'd like to thank the organizers first for giving me a chance to speak at this wonderful conference. I'm really enjoying my time here. So this is what I'm going to talk about, and this is based on this work with the same title with Bobby Acharya, Gordon Kane, Ran Lu, and Bob Zeng, and some general ideas. There's also a kind of a review which we wrote together recently, and there's some ideas in that as well. So this is the plan of the talk. So let me start with the motivations. So when one tries to connect string theory to the real world, which is what string phenomenology is supposed to do, one is led to the following conundrum, is that string theory seems to give rise to an enormous number of solutions which give rise to effectively four-dimensional universes. This property seems to be widely criticized by many people, especially in the non-string theory community, in that they say that the predictive power of string theory has been lost and string theory can predict almost anything. So in my opinion, however, the situation is of course challenging but not hopeless, and this is because of the following reason, is that although the landscape which I depict here is vast, it's not infinite, because it's actually a very small part of a much larger swampland, which is the set of all consistent looking low energy effective field theories which cannot be embedded in string theory. So this is my cartoon for swampland, and you can zoom in on the landscape. Now can we go further? So now you have to have a belief that if you believe that your vacuum is a solution of string theory, the vacuum which we live in is a solution of string theory, and in some sense, at least the people here in the audience do in some sense believe in this, because if we didn't, we wouldn't attend this conference. So if we believe in this statement, then there must exist a region in this landscape which gives rise to the standard model at low energies, or which reduces to the standard model at low energies, and is consistent with all known experimental and observational constraints. So this is this nice region of the landscape which I depict like this, and then the question arises, what typical features would one expect for beyond the standard model physics in this little corner of the landscape which is nice and pretty? Of course, we have to make some mild theoretical prejudices. With this kind of general philosophy in mind, more concretely, what we would like to do is we want to study some classes of solutions of compactified string theories which have the following properties. For example, in which the supergravity approximation is valid, the moduli are stabilized, the Kaluza-Klein scale is close to the Guth scale, and you have spontaneous supersymmetry breaking with superpartners around the TeV scale. So such solutions have been constructed in various corners of string theory, and also we have many examples in the literature, and we've heard many interesting talks on this conference with quasi-realistic matter and gauge spectra. And also in this previous talk, we heard that there's very nice ways of getting Yukawa couplings, including the CKM and PMNS matrices in corners of string theory like F theory. But in this talk, I'm actually focusing I'm actually interested in trying to understand properties of beyond the standard model physics which could arise within the class of solutions with these properties, and I'll try to focus in this talk on dark matter. The idea is in general to rely on very simple arguments, but which are general in the sense that they apply to a large class of vacua. So now in this class of vacua, what one can do is to try to make some generic predictions in this particular region of the landscape, and the crucial idea is that moduli physics plays a very important role, and was explained in very detail in these talks, so I'll be very brief. The crucial observation which we made is that the lightest modulus mass is very intricately connected to the gravitino mass, and so then the cosmological moduli problem gives rise to a lower bound on the lightest modulus mass, and by this connection it gives rise to a lower bound on the gravitino mass. So this has some very nice general consequences. First is that you have a non-thermal cosmological history before Big Bang nucleosynthesis, and because the gravitino mass is the order parameter of supersymmetry breaking, it constrains the scales of quarks and leptons in the 10 to 100 TeV range. Okay, so what about the dark matter predictions? Now, just from the fact that you have a non-thermal cosmological history, this gives rise to very qualitatively different predictions for dark matter than what you would assume in a standard from standard low energy, what you would naively expect from standard low energy arguments. So, okay, what are the natural sources of dark matter in this setup? Of course, since we have moduli, we also have axions, because axions are the imaginary parts of moduli. And in a generic compactification, we have a large number of moduli. This implies that we have a large number of axions, and which has been termed the axiverse. And of course, but you also have to stabilize the axions in addition to the real part of the moduli. And in this paper, we discussed a way to stabilize the axions in a natural way in which their masses were vastly suppressed relative to the gravitino mass. And one of them could naturally solve the strong CP problem and serve as the QCD axion. And you can actually also compute the abundance of these axions, because axions are also sources of dark matter. And it turns out that because of this non-thermal cosmology with axion decay constant of order the Gutt scale, you can still get axion abundance which is close to the WMAP measured abundance with a much less tuning of the misalignment angle. And the underlying reason is very simple. It's that the moduli decay dilutes the naive thermal abundance of axions. Okay. What about another? There is also another natural source of dark matter, which is WIMPs. And this is well known for a long time, that if you have any supersymmetric model which preserves some stabilizing, which has some stabilizing symmetry like R parity, then the lightest superpartner is a WIMP dark matter candidate. And in effective field theory, there is a well known traditional WIMP miracle in which the WIMP actually naturally gets the right order of magnitude for the abundance. But it turns out that there is a generalization of the WIMP miracle to the non-thermal case. It was first discussed in these papers. And the idea is very simple, that the number density which you have in the thermal case is actually enhanced in the non-thermal case by a factor Tf over Tr, where Tf is the freeze out temperature of the WIMP and T reheat is the reheat temperature arising from the decay of the lightest modulus. So since the number density is enhanced by this factor and the number density is inversely proportional to the cross section, this, to get the correct relic abundance or the correct order of magnitude, it favors a larger cross section relative to the thermal case. So a natural candidate for that in standard supersymmetric models is a Wino-like LSP, because with a mass of order the electroweak scale, because its cross section is naturally much larger than what is required for a thermal cross section. And with if you have a modulus mass of this in this range, then by using this formula you can roughly get the correct abundance. Now, from a top-down perspective, you can actually also get in vacua in which the gaugino masses are suppressed relative to the gravitino mass. You can actually find many examples in which you have a Wino-like LSP and a 10 to 100 TeV modulus mass. Okay, so from these general arguments, we are led to two non-negligible sources of dark matter. One is Wino-like WIMPs, and the second is axions. And this was predicted in 2010 in this paper in which we worked on the axions, and also in this broad review which came out a few months ago. And here we said, although we predict two sources of dark matter, the precise ratio of the abundances of these two sources could not be precisely computed with our current understanding of the theory. Why is it? Okay, so let me now come to the signal. Same day as our review was posted on the archive, another paper appeared on the archive by Christopher Weniger with this following title, which was very intriguing. And what he was talking about is the following. So this is a simple picture of the Milky Way galaxy, and this is the galactic center. And it's believed that there's a lot of dark matter in the galactic center. And once in a while, the dark matter particles annihilate and produce standard model particles, which include gamma rays, for example. And these gamma rays could be monochromatic, and the Fermi Large Area Telescope, which is up in the sky, could actually detect them. And what Christopher Weniger was doing was he was actually looking at the data of the Fermi-Lat satellite, and he found this tentative gamma ray line. So let me give you some details about this line. The signal that was this gamma line signal supposedly comes from a region of around 4 to 5 degrees around close to the galactic center. And a very interesting thing about the gamma line signal is that it has no known astrophysical backgrounds. The astrophysical backgrounds are a power law continuum, and the line signal just sticks on top of that. So it's easy, it's supposedly said to be a smoking gun for dark matter if you take into account all systematics. So this has been confirmed by independent analysis by at least 2 more groups, and especially this last one, the Harvard group, Fink-Beiner et al. This one is especially interesting because they do just a data-driven template analysis, and they find a significance of about 5 sigma. Well, you can ask, what about the official results from the Fermi-Lat collaboration? And they claim no signal in their most recent paper, but they exclude, in their analysis, they exclude regions less than around 5 degrees from the galactic center. So the positive results here and the null results here are technically consistent with each other. Of course, the final word will be said by the Fermi-Lat collaboration, and we eagerly await results in the region less than 5 degrees around the galactic center. And that would be very interesting if they have something positive. So if you believe that the signal is correct, then you can look at the flux coming from these from the galactic center, and the formula is given by this. There is some particle physics factors which depends on the cross section and the mass, and then there is an astrophysics factor which depends on the line of sight integral, or that depends on the dark matter density profile. The interesting thing about the line signal is because it's a line, once you know the energy of the line, you can determine the dark matter mass just from simple kinematics. So if it's a Z gamma signal, the mass of the dark matter particle is fixed to be 145 GeV. You can also do, depending on choosing the dark matter profile, you can also find the required cross section which could produce this signal, and you find a number like few times 10 to the minus 27. And a crucial assumption here is that WIMPs form the entire dark matter content of the universe. Now this is actually problematic for simple SUSY models and a thermal cosmological history, for the simple reason that in these simple models what happens is that this process is actually loop suppressed. So this compared to the total cross section, and so there is a usual one loop factor compared to the total cross section, and the total cross section in thermal cosmology is fixed to be this number to get the right relic abundance. So you get a number which is at least an order of magnitude smaller, if not more, compared to what is required. Yes. Now what happens, now I'd like to show that within this framework which I was talking about, it's very easy, or very nicely, the signal can be nicely explained. So as I said before, that you have some generic predictions for dark matter, that both axions and WIMPs have non-negligible abundances. So let me define eta as the global fraction of dark matter in the form of WIMPs, and eta GC is the WIMP dark matter fraction along the line of sight for the galactic center. In general, they are not equal, but they are roughly equal up to astrophysical uncertainties. Now the interesting thing is that since Winos have a much larger cross section, even though this diagram is loop suppressed, because the total cross section is much larger, the loop suppressed process can give you roughly the correct flux. And so when you put in this, and also the cross section is completely determined, because once you know the mass, only other parameter is the gauge coupling, the SU2 gauge coupling, which is known. So you completely know this cross section. So you, from the required cross section and the cross section which you get, and you use the flux formula in the previous case, you get a statement that roughly half of the dark matter is in the form of WIMPs, up to astrophysical uncertainties, of course, and the remaining is interpreted in the form of axions. Once you know the LSP fraction eta from this formula, from the usual formula for the relic abundance, you can also compute the reheat temperature, and you find that with a gut scale decay constant for the modulus, a string scale decay constant of the modulus, you get a gravitino mass of order 50 TeV. So everything hangs together, it's consistent. So now you can actually make falsifiable predictions for the future. If the signal is real and if our interpretation is correct, then you should actually observe gamma ray lines from the galactic center at energies of about 145 GeV from the gamma-gamma process as well, because right now we only considered the Z gamma process. And you should also observe diffuse gamma rays from dwarf galaxies. Are there also any falsifiable LHC predictions? And yes, there are, but you have to make some more assumptions. So until now the results were actually quite general because we didn't really assume any particular model of particle physics. But once you have a theoretical framework for supersymmetry breaking, if you have a Wino-like LSP with a mass of 145 GeV, it will strongly constrain other superpartner masses, for example the gluino mass. So to make more precise predictions, we have to choose some more details. We have to pick some more details. So in the remaining, I will study a particular framework, which is the M theory framework, in which we assume that below the compactification scale you just have the MSSM, and then we will look at the Wino mass, and the results are valid for the same framework, which gives the Higgs mass in the range, in the correct range, which was mentioned in Gordon Kane's talk. So just to mention that if you have a different theoretical framework, in principle the computation of the gaugino masses will be different, and so it will make different predictions for gauginos in general, so you can hope to distinguish among them. So this is the prediction. It's a prediction for the Wino pole mass as a function of the gravitino mass for two different signs of mu, and you find that you typically get something which is bounded from above by 1200 GeV. So this means that this should be observed by LHC in the near future if this kind of framework is correct. And the dependence on the sign comes from the sign of the threshold correction to the gaugino masses, and that's why they have two different predictions. And there will be more stuff on collider phenomenology in Ran Lu's talk. So the conclusions are that we are living in this data-rich era, which is great because that's the best thing we could hope for, and ultimately we have many abstract theoretical ideas, but at the end of the day it is important to connect them to data, because physics is ultimately an experimental science, and in this kind of work which I described, we have a pragmatic approach which allows us to make many predictions and which can be confronted with data. They're of course based on some assumptions. So, but the point is that the approach is actually very useful in both events, whether it agrees with data, whether it does not agree with data. Of course, it agrees with data, that's great. It will also justify the philosophy and the assumptions we make, and will provide insights about other fundamental questions. If it does not agree with data, it will tell us, depending on the nature of data, it could tell us which assumptions need to be relaxed and still provide a lot of useful insight. So thank you.
Time for a couple of quick questions.
Yes.
So what would be the prospect to directly
Direct detection
of this?
Yeah, so
not document at LHC direct discovery of W and Wino.
Oh yeah, that's a good question. So probably Ran will say more about it, but the thing is, so yeah, there is electroweak production of dark matter, of Wino-like LSPs will be, there is some, and this, I think by this year, until now the LHC is not very, has not been sensitive to electroweak production, but by data, they have been rapidly accumulating data, and by this year's data, they should be sensitive. So they should be sensitive to direct production of these Wino-like particles.
Light,
Yes, yeah, very light. So, yes. But you have to be careful about how they decay and look at all the cuts and stuff. So yeah.
Any other points? Okay, let's thank Piyush again.